on day one we were talking about definition for aeroacoustics and basics for aeroacoustics. Then we switched to direct computational aeroacoustics. Day two, yesterday, we talked about the acoustic analogy and the Fox-Williamson-Hawkins and the Gaussian noise modeling. So you have 3 workshops up to now. For day 3 you have also a workshop for broadband noise modeling, and we have 2 presentations, scalar resolving simulation and acoustic best practices and broadband noise modeling. Okay, so if I have a look now at lecture 5, okay, excellent. Okay, so we are going to talk about scalar resolving simulations, so the turbulent approaches that are available in ansys Fluent, where we are talking about scalar resolving simulations. Then we talk again about aeroacoustics, highlighting in fact the requirements and the best practices for using two kind of approaches, namely the direct CAA and the acoustic analogy with Fox-Williamson-Hawkins. And then we switch to some examples. Okay. So let's start first with scalar resolving simulations and the best practice. So I think you're certainly familiar with these turbulent approaches that can be used when you do some CFD calculation. Most of you would certainly know the Reynolds average Navier-Stokes models, which represent in fact nothing, which model everything. On the other end of the spectrum, you have the direct numerical simulation where you have no modeling. So that is, for example, we consider a mixing layer with 2 flows that are going inside a domain at different speeds. So high speed, low speeds, for example. You will have some interaction between at the interface between these 2 flows, and the interaction will create some specific eddies. So when you do Reynolds average Navier-Stokes modeling, you will apply the same modeling approach to all eddies. That is, you are going to diffuse, because usually in Reynolds averaging we are diffusing in fact the eddies. We are representing turbulence as a diffusion process. So we have no distinction between eddies. When we do Reynolds, we are applying the same treatment to all eddies. So you have some sort of diffusion which is due to this modeling of the turbulence. On the other hand, you have the direct numerical simulation. We have no modeling. That is, we try with the mesh, the grid we have, and with the numerics we exploit to represent all the eddies. So in this DNS, direct numerical simulation, we try to model, to resolve all the eddies that are appearing on the interface between these 2 flows. And in between direct numerical simulation and Reynolds average Navier-Stokes models, you have what we call the scalar resolving simulation. What is the idea behind this scalar resolving simulation? The idea is to model a portion of the spectrum. So you have very different size eddies, and when you do scalar resolving simulation, you will resolve a certain portion of these eddies, and you will model another portion. So usually you resolve the large eddies. That gives its name to the first method, which is given here, large eddy simulation. And then you will model the smallest eddies. So compared, for example, here to the image, a snapshot of the flow from DNS, we see that we lose some portion which correspond to very small eddies. So when you do LES, you do this, but you can also explore, investigate other approaches that are also scalar resolving simulation that try to do runs in certain portion and LES. It's what we call hybrid runs LES approaches. And when you do this, usually you call models such as DS, detached eddy simulation, its variance, SBS, specific to Fluent, stress blended eddy simulation, or SAS, scale adaptive simulations. So when you do this, you apply some kind of filtering. You will filter to determine, to distinguish the large eddies from the smaller eddies that you are going to model. So regarding the cost of the different approaches, when you do DNS, that means that you have tremendous cost for your computations, because you will solve, of course, the large eddies. It's not so big a challenge for the large eddies, but you will solve also the small eddies. It's a big challenge. Why? Because they are small, so you need a very fine mesh. And in fact, 99% of your efforts will be resolving these small scales. So that is why this method is so expensive, because you will try to resolve the large scale, but also the small scales. And small scales are very difficult to solve, very expensive. So DNS at this point, it's a very useful tool, but for research. So usually for industry, it's too early for DNS. We don't have the computational resources to do DNS at the moment. So we usually revert to RANS or scalar resolving simulation. RANS is the most widely used approach in industrial CFD. Why? Because it's cheap in terms of grid. So usually you have a small grid. You can do usually with RANS, you can do a steady state simulation. And if you do an unsteady state simulation, it's what we call URANS. You can have solution for that, but usually it's a steady state solution. So that means that you don't have any temporal term to resolve inside your equation. So it's a bit cheaper in terms of modeling as well. And in between DNS and RANS, you have scale resolving simulations. And here also it's beginning to be affordable for industrial computational resources. So more and more people are doing now LES, DS, SBS, and so on. So when you do this, remember one thing is that scale resolving simulations will be inherently 3D and unsteady. 3D, why? Because the LES portion of your calculation, if you do hybrid RANS LES, the LES requires to capture 3D and unsteady eddies. When you talk about turbulent eddies, they are 3D and unsteady. So it's usually great amount of computational resources to capture all these eddies. So it's not so important as for DNS, but it's still important. So remember that when you are in the industry, you will use usually RANS, and if you want to increase the accuracy of your simulation, you will switch to scalar resolving simulation, and you have more time, you have more resources. It's a different kind of calculation at this point. So we are going to focus our attention on the scalar resolving simulation in this presentation. I was talking about LES, but also in fact you have hybrid RANS LES. So it is exactly what is represented here. You have RANS here with a classical model, two equation models, RSM models, stress models, and so on. These models are available in ansys, and on the other side, for large eddy simulation, you have what we call SGS models, subgrid scale models. And it points to very classical models such as Smagorinski, which is very old, 1963, and you have some variants. Whale model will adapting local eddy viscosity, dynamic Smagorinski, K equation as well. So it's clearly these models that are available for the LES portion of your hybrid RANS LES models. So when you do scale resolving simulation and hybrid RANS LES models, you will try to combine the best of these two approaches. So for example, when you do DS, SAS, and whole model LES, you will let the model in fact determine the portion of the domain or computational domain that is solved with a RANS approach, and the other portion that is solved with a LES model. And it's done automatically. That is, the model will detect, in fact, the walls, your walls. It will say over a certain distance from the walls, I will do RANS. I won't do LES. Why? Because as you get closer to your steel wall, the eddies are beginning to be smaller and smaller. At certain points, they are so small it's difficult to capture them. So what we try to do is we try to decrease in fact the cost of resolving all these eddies and saying, I will do RANS near the wall. So you switch to RANS near the walls, then you have a gray region that will to be extremely small, where you will switch from RANS to LES, and in the core flow that is far from the walls, you will switch to LES with SGS models I was talking about earlier. That is defining, in fact, the automatic models, hybrid RANS LES, with an automatic process to switch from RANS to LES based on the wall distance. And then you have the non-automatic approaches, which are called, in fact, embedded LES in Fluent, and which correspond to the user defining the RANS region and the LES region. So that means that you can have a complete volume, even far from the walls, where you do only RANS. And then you switch to a LES approach to represent another portion of your domain. But it's your choice. That is you, as a user, that is defining the two different domains. And it's what defines, in fact, embedded LES. But remember one thing, when you do RANS, you can have a coarse mesh or coarser mesh, but when you switch to LES, you need to be careful because the size of the grid cells will control, in fact, the eddies that you will capture. So the grid is most important for LES approaches. So when we do SRS or URANS for aeroacoustics, we don't have the same. We don't have the same purpose in mind, because when we do SRS, we know that we have to consider a very fine grid, and when we have this fine grid, we are going to recover, in fact, a large spectrum of eddies. So that is exactly what we have here. TSR4 flow arriving on TSR4, creating a stream of eddies, which is captured in SRS, not captured in URANS. And behind this, if you place a probe to capture some variation of acoustic pressure, for example, you can recover some creation of sound in an SRS calculation, but only if you have the proper mesh definition. So you need to be careful. If you don't have the proper mesh definition, you will miss all this acoustic information because you will damp it, as we saw previously. So URANS most often they fall short of capturing the remaining large scales that govern the unsteady flow characteristics. Because why? Because in fact the eddy viscosity that is used for URANS is usually too large compared to the viscosity that would be necessary to capture this eddy. So usually it's too large in URANS, and it completely damps the propagation, the creation, and even the propagation of these eddies. And we know that these eddies can contribute to noise generation. It's usually a color pole source, for example. So when we do this URANS calculation, we know that we are going to dissipate these acoustic waves. We know that we dissipate turbulence structure, small turbulence structure, but we know also that we dissipate noise that is created from this turbulence structure. So for practical LES, there is a limit. Why? Because as you can imagine, with the high Reynolds number, you will capture more and more eddies. The higher the Reynolds number in your simulation, the larger will be the number of eddies that you can capture inside your simulation. But you can, I said you can, because you still need a very fine grid to capture all these eddies. If you don't have the correct grid, you will not capture these eddies. Even if you have this high Reynolds number, you will miss a large portion of these eddies on the spectrum. So, in fact, with computational resources today, it's difficult to go beyond Reynolds equal 10 to the power 4 or 5 for wall banded flows. So remember this limitation, keep in mind this limitation, because it's important when you do LES. But we were talking about LES for hybrid RANS LES models. Usually it's better, it's easier. Why? Because when we do these approaches, this combination of RANS and LES, we are going to resolve the motion of these large eddies, but far from the walls, because we know that near the walls we are going to create some small eddies. And it's quite expensive for LES. So for hybrid RANS LES, we combine RANS near the wall and LES in the core flow. So you will have a reduced computational cost for capturing all these eddies in the boundary layer flow. Why? Because in fact you are not capturing them, you are modeling these eddies. You are modeling a contribution from the boundary layers inside the core flow. All the idea is to properly define this contribution from the RANS up to the LES, to properly feed the turbulent content inside the LES calculation. So here you have an example of hybrid Lorentz LES calculation, you see that you have a large amount of eddies that are created, not everywhere, it's highly anisotropic, this creation of eddies. And point is that you are not capturing the eddies that are creating near the wall. Near the walls, we are going to completely model the turbulence. So that is, we create some turbulence information a bit further from the wall, that is, a bit away from the boundary layer near the wall. The idea behind LES represented here on this simplified 1D turbulence spectrum. So regarding, we compare energy versus a wave number, which is in fact an inverse measure of the eddy size. We have energy containing eddies, which correspond to large eddies, and then we transfer energy along this subdomain, inertial subdomain. And when we do this energy transfer, we are transferring a large amount of energy from large eddies to smaller and smaller eddies. And as we know, there is only transfer and no loss of energy. To accumulate all this energy, to get all this energy, these smaller eddies need to move faster and rotate faster and so on. And at a certain point, there will be some dissipation that appears because the eddies are rotating, moving too fast, and they dissipate in fact in the flow. But it is not what's happening in LES. In fact, we place the grid limit a bit above this limit, which is in fact Kolmogorov length scale. So when we place the grid limit for this LES calculation, usually it's at a fixed length for the grid sizing, and this size is usually not the Kolmogorov scale, but a little above the Kolmogorov scale. Here, for LES, all the idea is to have a sufficient number of eddies that are created to properly represent this cascade process, this Kolmogorov cascade process. Yes, at this point it's a nice variable to introduce. I don't know if you're familiar, but Stephen Pope introduced some time now ago a criterion, in fact, to produce a simple measure of the turbulence resolution in the resolved motions. So this is the criterion, the Pope criterion, M, which reads, and you have the definition here, where in fact it's a ratio between the turbulent kinetic energy of the subgrid scale eddies, so the modeled eddies, and the total kinetic energy, both from the modeled eddies and the resolved eddies. And when you consider this ratio, Stephen Pope suggested some values which correspond to good resolution for your LES. When you do, when you have this value of m equals 0, that means that you are not modeling any kinetic energy from subgrid scale. That means that you are doing DNS, in fact. When you have m equal 1, typically it means that you are modeling everything, because everything is inside the AGS. So that means that you are modeling everything. You do runs, in fact. So it's a good measure in function of this value of the kinetic energy content that you capture within your simulation. And so at this point, Pope suggests to have a value of m equal to 0.2 to resolve, in fact, explicitly 80% of the total kinetic energy. So it's a good measure. So keep in mind this value is quite a good indicator of the quality of your grid. So if we try to define more clearly what it means in terms of grid sizing, for example, if we consider this limit of m equal 20%, so that means that we want 80% of the total turbulent kinetic energy to be solved. We represent, in fact, ideally the turbulence spectrum, and we want to have a ratio of energy which is solved around 80%. That means that we'll have some limits on the minimum eddy that we want to capture, and the limit will be around 42% of the integral length scale. The integral length scale is a measure of large eddies, the size of large eddies. So when we do this, we know that we want to capture an eddy which is 40%, something like that, of the integral length scale eddy. And we want across this eddy a certain number of points to capture it properly. So it's important to see. So At this point, when you do your first RANS calculation, you can assess, in fact, through your RANS calculation, the integral length scale. We need to have at least 5 cells across this integral length scale to resolve 80% of the K spectrum in the regions of interest. So we have 3 methods at this point. We can crudely estimate the integral length scale based on the size of the bluff body and a correlation. You can use another empirical correlation if you have one, not based on the size of bluff body but on local property of turbulence or mean properties of turbulence. Or you can perform a preliminary RANS calculation and compute the integral length scale from available turbulence quantities that are defined from your converged solution. So that's what is done here. For example, you have some GUI windows that represent some custom field function calculated inside Fluent directly. So imagine you are doing your RANS calculation, you have converged this calculation, you have a field for all quantities, that is, for example, for turbulent quantities. And from these turbulent quantities, you are going to extract an approximation for the integral length scale. This is exactly what is done here. So here you recognize you have the turbulent kinetic energy, K, and the specific dissipation rate, which is in fact omega. It's typically a k-omega calculation, and based on this quantity you are going to define an integral length scale, which is a local value because these quantities are local. And in the same idea you are going to estimate the cell size. So usually your cells are not cubes, perfect cubes. They have a certain shape, so what is usually suggested is to consider the third root of the cell volume to extract this cell size. So that will give you an order of magnitude for the cell size, a characteristic cell size. And here, what is doing the user is already creating, in fact, the ratio between the integral length scale and the cell volume. And based on this ratio, it would be able to assess, in fact, the correct resolution for its calculation. All the idea is to have a ratio which is nice, that is this ratio which is above 5. So here, for example, you see that you have under-resolved the mixing layer and you have the ratio which is well below 5. So you need to refine this calculation typically. So that is one of the questions you will ask yourself when you do LES, how to define the grid sizing. Here is another question that could be raised when you do LES calculation, and this is when your domain is limited in terms of extent. So at some point you will have some frontier of your computational domain, and at this frontier usually you will need to input to feed some turbulence. So to do this, we have different methods. So it can be interesting, for example, for a pure LES calculation, but it can also be important when you have an embedded LES. For example, if you have a URANS LES interface, that is a portion of your domain that is represented with a RANS approach, and another portion of your domain which is represented with the LES approach, you will have an interface in between. And problem is that URANS is not creating sufficient turbulent eddies. Why? Because in URANS, if you remember, I was talking about a turbulence model applied to all eddies, and usually these turbulence models create some diffusion. It's not representing explicitly the motion of these eddies. So at the interface, we want to switch to LES approach, and when we want to switch to LES approach, we want to feed the LES with a proper level of eddies, but we want to feed with a proper of explicitly resolved eddies. We don't have them, but we are going to evaluate them from the incoming turbulent information that comes from the URANS calculation. So we are going to use the URANS properties and the interface, and then we are going to feed artificial turbulence. So you have different methods to do this. You have the vortex method, which depend on the mesh resolution. You will create coherent structures that preserve, in fact, turbulence levels at the interface. You will have a spectral synthesizer with no spatial coherence, which is important, and you have the harmonic turbulence generator, which is less used at this point. Both methods, both the first one, are preferred today. Vortex method is even more recommended. It's usually very easy to use. You just evaluate the number of cell faces that you have at each of your inlets, and then you set a number of vertices for this vortex method to n divided by 4. There is a maximum of vertices you can create with this method, which is around 1,000. So here at the interface, this vortex method we create based on the local properties of turbulence and flow velocity field. We create a certain amount of eddies. These eddies that we are capturing here, for example, on this image. Here you see that in Urance you're not capturing any eddies, but at the interface, because of the vortex method, we feed the domain with artificially created eddies. And then these eddies will interact with the eddies that are properly represented inside the LES calculation. So you will have a proper interaction between these. Okay. How to check? Because okay, I have some idea of the LES sizing in my LES region. I know now that I must feed some turbulent content at the inlet or at the interface between my RANS and LES calculation, but how do I check afterwards the quality of my results? Are there some indicators to evaluate this? So here you have a first indicator. In this situation you have an obstacle, you have some flow arriving at this obstacle, creating some wake flows. And we expect this wake to be turbulent if the inflow velocity is sufficiently high. So for example, in this situation, you have the grid, which is represented here. It's an hybrid grid. You have some polyhedral mesh, some refinement near the obstacle, but no refinement behind the obstacle afterwards. Downstream of the obstacle, you don't have any particular refinement. It could be a problem. Let's check that. One first indicator is to plot, to display in fact the viscosity ratio, which is in fact the viscosity ratio mu SGS over mu fluid, which is water here. So you compare in fact the value of the eddy viscosity for the SGS contribution to the viscosity, the dynamic viscosity of your fluid. And this ratio, usually for good SRS in LES portion, it should not exceed 10. So it's usually a good value. And here, for example, we plot the LES subgrid turbulent viscosity, and we see that we reach rapidly in the wake values above 10 times the dynamic viscosity of your fluid. So it's not a very good indicator. It indicates at some point that you have missed a little of resolution for your grid. So, okay, it's a first indicator something is a bit wrong in your simulation. So let's try to identify in a different way this loss of information from the eddies in the wake. So you have another mean to do that. You can place in fact a probe in the wake. So we place a probe in the wake where the grid is a bit unrefined, and then you will have this situation. So you will have this situation. You have you are at the probe. You are extracting in fact the velocity. You are plotting in fact the spectrum of velocity versus frequency. And what you observe is in fact a dissipation, a rapid dissipation of the velocity in this probe. So this is not the correct trend. Why? Because when we do this kind of extraction in the wake, which is supposed to be extremely turbulent, we know that we can expect a trend of decay for the velocity spectrum, which is following the Kolmogorov inertial law. And this Kolmogorov inertial law says that you will have a trend with a slope of k steeper. That means that we are diffusing very rapidly the kinetic energy content. Here, at this probe. So this is a good indicator that here you have a problem. You are dissipating too quickly all the turbulent information you have at this probe. So to solve this issue, at this point, best is to refine the mesh. So that's exactly what has done the user here. You still have the obstacle with a refinement, local refinement corresponding to near wall flow. And then you have a region around the obstacle, a bit further extending downstream, where you are going to refine all the cells. And then you have further refinement and so on. So compared to the previous mesh, clearly you are refining a lot the mesh. So you will have finer cells to capture finer IDs. And that's exactly, it translates exactly on the subgrid scale viscosity level. You see that now you are clearly well below 10, this value of 10, regarding the ratio between the subgrid scale viscosity and the dynamic viscosity of your fluid. So this is a good indicator, things are getting better. So let's start to have a look on the dissipation spectrum. And here, once again, if you place a probe here in the refined region, you will see that the velocity spectrum is showing something much nicer. We are close now to the Kolmogorov inertial law, k to the power minus 5/3. It's clearly an indicator that things are going better, and you see that you are capturing a larger number of eddies, and these eddies are dissipated at the correct rate. So for spatial resolution, some hints, and now for time resolution, you have also some constraints to keep in mind. When you do LES, usually temporal resolution should match or exceed the spatial resolution in LES. So you have some CFL condition, and usually the CFL condition translate to current number. Already so, but remember when I was talking about this current number for the second lecture on direct computational aeroacoustics, remember there was a clear difference. The clear difference was I was not considering the flow velocity but the acoustic speed of the wave. So this is different, so you need to be extremely careful at this point. We are talking about the current number for the flow velocity, so you don't see any contribution for the acoustic speed. So this is important. This means that this constraint is only for the CFD, the aerodynamics. And imagine if you have these constraints for aeroacoustics, and if you are in a low Mach number flow, you will have a constraint which is much stronger. Why? Because the value of the speed, the effective speed you are going to consider will not be U but U plus C. And U plus C, as you can imagine, for low Mach number flows, U plus C is far larger than U only. So remember, this constraint is only for the LES and for aerodynamics. When you do aeroacoustics, it will be much more difficult to respect this constraint of current number. And we are talking, in fact, about an acoustic current number. So here the constraints for the aerodynamics below 1 for this ratio U delta T over delta X below 1. So if we make some summary of the different approaches, the main approaches we saw, LES, of course, it depends on time and space discretization. It directly resolves the large-scale turbulent eddies. All the idea is you have your mesh. If your mesh is sufficiently fine, you will capture a large amount of eddies. And if your Reynolds is sufficiently large, you will also have a large number of eddies. So you need to have the proper mesh, the proper grid resolution, but also the proper Reynolds number. If your Reynolds number is too small, you will not capture eddies because physically they are not created. And at a certain size, which is in fact influenced the cell sizing, the local cell sizing, you will introduce some grid limit, some grid filter limit, and at this grid limit you will introduce some dissipation. It's what we call an eddy viscosity model for subgrid turbulence. So that are the fundamentals for LES. The advantages are clear. You accurately resolve large-scale turbulence. You properly, explicitly resolve this large-scale turbulence, and you provide a modeling on a smaller portion of the spectrum. And in fact, it's even more satisfying than that, because these smaller eddies tend to be more isotropic. So usually, the SGS models are quite simple to write, and they apply more easily to these small eddies, because we know that these small eddies are usually more easy to represent because they are more isotropic, more universal in certain terms. Okay, the drawbacks are obvious. You need a 3D mesh you need a 3D fine mesh usually. You are going to do an unsteady calculation. You have a strong requirement on CFL, so it's not that easy in fact. You need, so of course, LES resolution inside the domain. You cannot coarsen the mesh too fast, for example, because you will lose some turbulent information, and if you lose this turbulent information, it's difficult to recover it properly afterwards, so you need to be careful. And you need also additional description for near-wall turbulence. It can be very sensitive, of course, to grid resolution, but also to the turbulent content that you feed at the borders or at the interface between RANs and LES. And it's very limited in terms of Reynolds. Why? For wall-bonded flows, you will have severe problems near the walls, because the ADs will get smaller and smaller near the walls, and it can be extremely difficult. So as you can imagine, you have high computational costs to run the simulation, but also high computational costs to store the solutions. This is a point that is usually missed or forgotten. You have a high computational cost to run, but also to store, because when you do LES, you're also doing some transient analysis of the flow. And when you say transient, that means that you will have several snapshots of the fields of the quantity, special fields of the quantity, and that means that you will have a large number of solutions. Whereas, for example, for RANS calculation, usually it's nice to have only the converged solution that makes one compared to large number, because you want to animate the flow to see the unsteady characteristics of the flow. So the typical scenario of usage for LES is when you want to study highly unsteady turbulent flow characteristics, for example, turbulent wake flow, aeroacoustics, of course. Many situations when you know you have a large amount of ADs that are created. In fact, many industrial situations can benefit if you want to have the details of this transient phenomena. But usually it's very expensive to do LES, and so we revert to DS, and you have some variants for DS as well. So DS standing for detached estimation. It depends on time and space discretization. You will have a portion of your domain that will be solved using RANS, and another portion which will be resolved with LES approaches. When you do DS, this separation between RANS and LES will be done automatically based on the distance to the wall. So when you do when you have a fine grid region far from the wall, you will obviously switch to LES, and the computational effort compared to LES is much reduced. Why? Because you will have a coarse grid RANS near wall grid, which is in fact affected only by the model, the RANS modeling you are going to use in the near wall region. For the drawbacks, obviously in the near wall region, the near wall turbulence that you are going to calculate will have an impact on the core flow. It's very sensitive in fact to the transition between the RANS and the LES region. So usually it's not so easy to shield in fact the RANS region near the wall, and that's why we developed at ANSYS some different approaches, variants of DES to better shield this RANS region near the walls. And another drawback, obvious this time, is that this calculation is still unsteady. That means that you still need some storage space and some computational resources, which are not negligible. Recommended usage are typically the same as for LES. SBS is more advanced, it's part of the DES family. It's another method which is extremely interesting because it switches properly to LES model with a proper SGS modeling inside the core flow. So you switch from a RANS, pure RANS, to a pure LES approach, typically. You have an asymptotic shielding of the RANS boundary layer. The switch is explicit in the LES region, and you have a rapid transition from RANS to LES. The transition is extremely rapid, and it's a good sign, it's a good property, because you want to have less uncertainty possible at the transition between RANS and LES. You want to do RANS or LES. You don't want to do a mix of these two approaches. And now it's also possible to display easily RANS and LES region based on the shielding function. So SBS is one of the first models that allows for SRS hybrid RANS LES, that allows one user, in fact, to clearly see the regions solved in RANS mode and the regions solved in LES mode. Drawbacks are the same as previously. The recommended usage same to TS. Usually you want to study the flow characteristics when you do this kind of calculations. SAS, same idea. The main idea I would like to say about SAS is its own advantage is that you have a safe hybrid model. That is, when you do SAS, you will have a model that reverts automatically to k omega SST when you don't have the correct grid resolution, and that is particularly true in the core flow. In the core flow, if you don't have a correct fine grid resolution, it will safely transition to k omega SST, and that is a property that is quite interesting when you cannot represent the correct eddies everywhere inside the core flow. So it's a nice property of this model. But as a main drawback for this model is usually for this model it's nice to have a clear flow instability that generates resolved turbulence. If you don't have that, usually you don't have enough generation of turbulence, and you cannot switch to a sufficiently large spectrum of eddies, and then it will be the weak version of the SAS that is used, and that is the RANS classical k omega SST that is used. So you need to be careful with that. For aeroacoustics, we have finished with FRS. For aeroacoustics, it will be the same guidelines I gave to you previously in the previous days. We'll review these guidelines just to be sure that you have the correct input for these guidelines. We recognize some guidelines because I already talked about these slides earlier. So challenges, yes, remember, magnitude of acoustic waves very small compared to aerodynamic pressure. So remember, when I was talking about the acoustic pressure is significantly lower than even the atmospheric pressure. So you have a large discrepancy between these values for pressure, but also for other quantities. It's also true for the fraction of the energy of the primary flow. The acoustic portion of the energy is extremely small compared to the energy which corresponds to kinetic energy or so on. So it's clearly small quantities. When you talk about aeroacoustics, you are talking about very small quantities. Another problem is that when you are talking about aeroacoustics, you are typically talking about unsteady phenomena because you are propagating an acoustic wave. So it's clearly an unsteady phenomena. It's difficult to represent with a steady approach, nearly impossible, because the constitutive equation for acoustic waves propagation, it's clearly an unsteady equation with a temporal term, which is quite important. The frequency range of interest, remember when I was talking about the human ear, the frequency range of interest is 20 to 20 kilohertz. So that makes quite a large range with different orders of magnitude, and usually it's better to use a decibel scale which is based on logarithmic consideration. Yes, we talked about this one a few times now. Let's review this one once again. Monopole, dipole, quadrupole. Remember these sources, it's important. For low Mach numbers, remember that monopole is the strongest source, stronger than dipole and much stronger than quadrupole for low Mach number flows. Monopole corresponds to a variation of a mass flow. It's a fluctuating fluid volume that is creating, in fact, this sound. So here you have the classical representation of a monopole. The dipole is the interaction. It's usually a variation of surface efforts over some surface. You will have some interaction between the flow and this surface, and we create some dipole contribution. So created by flow around solid objects and so on. And for quadrupole, remember, we are talking about turbulence mainly. When I talk to you about the quadrupole contribution, it's complex contribution, many eddies that are interacting between them. Typically, it's fluctuating shear fluid particles when you have turbulence. So usually a small contribution for low Mach number flows. Yes, we talked about this tables in the first presentation. Let's go back just to see the main difference between all these models. Yes, you remember direct computational aeroacoustics, expensive computation. Typically, it's a very expensive computation, but you can account for complex effects. Reflection, effect of sound on flow. Solution scheme is always transient, of course. When you do direct CA, you are doing a transient calculation, as accuracy is usually very good. It's not perfect because you are not taking into account, for example, vibrations in the solids when you do this kind of calculation, but it's still very good. Very, very good. Fox-Williams and Hawkins, we talked about it yesterday. It's fair computational costs, but particularly compared to direct computational of aeroacoustics. You do not account for reflection or effect of sound on flow. So this kind of limits, you remember, it's entirely due to the use of the acoustic analogy. But when you use the acoustic analogy, you still are going to use some wave equation. And when you say wave equation, you say transient resolution. The accuracy is usually good. Lawson-Guttin, we talked about that. It's limited to steady-state analysis based on the Fox-Williams and Hawkins. The model analysis, it's a better feature to extract some information on acoustic modes inside cavities, for example. You have broadband noise modeling as well. I'm going to talk about this in more details in the next presentation. And here what is presented is a third-party coupling one way, or when you do in fact a CFD simulation and then you extract the result to feed another code, a third-party code that will solve for you only the acoustic parts, the acoustic portion. Yes, we were talking about SRS scale resolving simulations, and typically when we talk about scale resolving simulations, we address in fact the first two methods, that is direct computational aeroacoustics and Fox-Williams and Hawkins. So when we do this, when we review all the models inside this table, one important point is that you decrease computational effort, but you also decrease accuracy when you go from direct CAA up to broadband noise modeling. So broadband noise typically is very cheap, as we see in a moment. It's very cheap, but it's not very accurate. Accuracy is very limited, so you need to be careful. You get what you pay for. When you pay for a very accurate model, you will pay in terms of grid, computational resources, storage, and so on, but you will have a good accuracy. It's a fair reward for all this cost that you are paying. But when you do broadband noise modeling, typically it's very cheap, but it's very limited as a response. For third-party coupling, you have usually dependence over the methods, because we'll see that there are different methods that can address in fact the acoustic part of the problem. So depending on the methods used for the acoustics, you can have a calculation which is more or less long and can be more or less accurate based on this method that is taken into account. Yes, this one is, we already saw this one as well. Many points that are important based on the life, I would say, of an acoustic wave. First, you create the acoustic wave, that is a information, so you want to know do you have, where they place between them, the strengths of each sources relative to the complete source region. Once you have all this information, you want to propagate the sound. Acoustic propagation in the medium. Are the properties of the medium varying along the path of this acoustic wave? So these kind of questions are very important to correctly represent the acoustics. And then where is located the receiver? Do you want to receive extremely complete information with discrete and broadband noise components? Do you want to have some information about directivity? What is the length of the signal you want to recover? All these kind of questions must be addressed. Yes, yes, we already saw this one. It's more clearly represented. We are talking about CAA, direct computation of aeroacoustics. Here you have an acoustic wave, the wavelength lambda, going at a speed of c, sound speed, and here we consider in fact different calculations. So with CFL inferior to 1, but a poor spatial resolution, that is the wavelength divided by the cell size is only equal to 10. Remember, it's not that sufficient. I was more talking about 15 to 20. Even with CFL equal 0.5 or 1, that is red curve and green curves, we're comparing the velocity magnitude compared to the position of the wave. We see that we have some issue with the Gaussian pulse. We see that we have some issue because we are not propagating the correct amplitude for this Gaussian pulse. We have the correct positioning for the Gaussian pulse for this CFL inferior to 1, but the amplitude is clearly completely missed. We are missing a portion of the amplitude. So this is entirely due to this poor discretization, spatial discretization of the wave. On the contrary, when we have correctly resolved wavelength with 25 points per wavelength, with CFL inferior to 1, CFL equal 0.5, 1, green and red curve, we recover the correct amplitude. It's a bit less, but globally it's correct, it's correctly placed, and the amplitude is not so far from the initial amplitude expected. But when you increase the CFL, you see that you still encounter poor results. You still see some diminishing of the peak of the wave, but also you see some dispersion errors. You see that you have high frequency components that appear. It's entirely due to this CFL condition, which is not respected anymore. So you need to be extremely careful in that, because spatial resolution is not sufficient. You need also time resolution, correct time resolution. Yes, I already talked about this one on session 1, always the same case. With the variation of the wall, the positioning of the wall changing, so it is creating some variation of local pressure. It is creating, in fact, an acoustic wave, and you see that when you don't have the correct spatial resolution, you have poor spatial resolution with the wavelengths discretized with only 11 points. You are not correctly propagating the acoustic waves. They are damped, in fact, so you need to be extremely careful here. Yes, I was talking about these non-reflecting boundary conditions. Remember this monopole source, which is creating some waves, and these waves, when you use non-reflecting boundary conditions, they are not reflected. So you don't have any waves coming back up to the monopole. With a non-reflecting boundary condition, static pressure, no information getting back inside the domain. Without this non-reflecting, typically you will have this phenomena if you arrive on an acoustically open boundary condition. For example, you have a pipe and you arrive on a very large atmosphere, a very large plenum, you will have this kind of behavior that will appear. Okay, yes, we already saw this one. Just some reminders when you set up your calculation for direct CAA. The importance particularly to define, in fact, the correct boundary conditions at the borders of your domain. Sponge layer, which is also important. Check the level of CFL at the inlets and at the outlets, because it will affect, in fact, the acoustic waves that are arriving. Avoid using Pasto scheme for pressure because it delays eddy generation. Prefer standard or second order schemes for time discretization. Nothing less, in fact, than second order. And for a boundary condition, prefer here in this situation when you have a jet inside an atmosphere and you cut your domain at some point, prefer non-reflecting boundary condition. It's necessary if you don't want any acoustic information going back inside the domain. Sponge layer, yes, remember this one. Sponge layer may help to recover proper acoustics inside the domain. Another view, in fact, of these requirements in terms of this small graph, plotting frequency versus distance between source and receiver, you have two situations. In fact, you have a very high frequency but a low distance between source and receiver. So it's still doable. That is, you will have a very small domain. You can grasp very high frequency acoustic waves because you are not going to propagate them on a large domain, because the distance between source and receiver is small. And on the contrary, when you consider very low frequency, very slow acoustic waves, not with properties that are evolving very slowly during time, distance between source and receiver can be larger, much larger, because you have time. You have time to capture. In fact, you have the acoustic wave is easy to capture because it's not evolving very fast. So it's another situation when you know that you can represent, in fact, the propagation of the acoustics. But in between, you have a large domain where it's becoming very difficult to capture because you still have a high frequency, but the distance is increasing, and usually it's very difficult to capture, in fact, the proper propagation of these acoustic waves. So that's why usually it's very limited to use direct CAA, because we know that we will still have very strong issues when we consider large domains on very fastly evolving acoustic waves. So we need to be certain that we have the correct computational resources to represent these kind of problems. And that's why usually the problems must be limited in terms of extent and also in terms of time step. Yes, that was all for direct CAA. For Fox reamps and Hawkins, I will do some I will remind you of some guidelines. Remember, I was talking about Fox reamps and Hawkins yesterday. When you do Fox reamps and Hawkins approach for your aeroacoustics, you are using, in fact, the Lytle's acoustic analogy. So it's propagating, in fact, noise sources in a uniform fluid at rest. We are going to represent the propagation of this acoustic information using a homogeneous wave equation. The acoustic and the aerodynamic fields are, of course, decoupled. That is, you are going to consider a domain, a source region, and at the borders of this region, you are simply going to propagate with an analytical solver the wave equation up to the receiver. So that means that along the propagation path, you won't have much change because we are going to use an homogeneous wave equation. So you have the simplest form of the wave equation to represent the propagation of this information from the borders of your acoustic source. Yes, there are three contributions for the Fox reamps and Hawkins representation of the acoustic information. So you have a first contribution, which is the volumic integral. When you see the volumic integral, it's clearly the quadrupole source that is involved. And when you speak about a quadrupole source, so we recognize here the Lytle's tensor. We know that it's related directly to the turbulence inside the source region. And then you have two other contributions, the loading noise and the thickness noise. Talking about loading and thickness noise, we are talking about, in fact, surface integrals. So when we talk about these two contributions, it's two surface integrals, and you have a dipole contribution and a monopole source contribution. It's based, all these two sources are based at the source frontiers only. So the source, the integral that is performed here is the integral over the surface that are corresponding, in fact, to the borders of your source region. Yes, you can consider solid walls and also permeable interior surfaces. You can do the analysis considering these two sets of surfaces, remember. A quadrupole term is dropped for low Mach number. So when you do permeable porous surfaces, you will consider quadrupole contribution inside the domain up to the frontier, but after the frontier, you are not going to propagate this information anymore. For solid source surfaces, you won't have any quadrupole noise contribution. We talked about it yesterday. Yes, this one as well, regarding the length of the signal. Remember, always consider in fact the period of the phenomenon you want to take into account, and based on this period you want to consider a large number of these periods, to have a proper accuracy for your signal. For example, here for the rest signal, the acoustic signal for acoustic pressure is too short. You don't have enough periods of phenomenon you're interested in, and then you completely miss this phenomenon. If you have a look at the spectrum, it's much too coarse. You don't have enough information at this length. Let's go through some examples. Yes, this one, cavity noise. Have a look at the Mach number, a bit below 1. We are talking about DS, so this SRS approach. Remember, runs in the near wall region and then LES in the core flow. Time step size is still very small, 20 microseconds. Grid is not so high, but it's still important with hexagonal cells, 7 million hexagonal cells. Here you have an overview of the Q criterion, isosurfaces of Q criterion. It's usually a good marker for eddy cores, colored by the eddy viscosity ratio. And we try to recover some cavity noise in some probes placed inside the cavity, and you recover some pressure level in decibel, comparing experiments in blue and fluent, SAS in red. Agreement is quite nice. You still miss some contribution for broadband noise, but it's quite nice in terms of agreement. For Savio mirror, it's a completely different kind of source emission, because it's the obstacle and it's a wake, a flow of this obstacle that is this time creating, in fact, this acoustic content. So free stream velocity 140 kilometers per hour, so Reynolds is quite high, around 500,000 based on the diameter of this Savio mirror. Grid only 3 million nodes, SAS, time step still 20 microseconds, and here we say the same idea as before. We place some probes and we recover some spectra. Some sound spectra, some pressure level versus frequency. It's a logarithmic scale, and you see that for low frequency signal is sufficient to recover the proper level, but for broadband noise corresponding to higher frequency, we miss some information. We don't have the correct generation of these eddies at this point, so we miss some acoustic information at this point. Yes, to conclude, for SRS, remember, we are talking about 3D and steady calculation, so very high computational costs. LES is quite expensive, particularly due to the fine mesh requirements. And when you do hybrid SRS, you compensate this requirement, because you say that near the walls usually you will do some runs, and when you do some runs you have a coarser mesh, because the requirements are not the same for runs compared to LES for the near wall flow. Regarding aeroacoustics, yes, large discrepancy between aeroacoustics and aerodynamic flow quantities, particularly true for the energy, the pressure, and so on. Sound field, usually you will be interested in listening from a very far position, very far locations. Usually the domain should be extremely large if you want to take into account receiver which is far from the source region. So that means that you will have a large domain. And sound generation and propagation are two different problems, but they need to be treated both, because when you generate the sound, this is the first step, but you still need to propagate the sound. And the propagation inside the medium is also an important problem. So SRS and aeroacoustics can be combined in the two following methods. The direct computation of aeroacoustics. Remember the costs, the requirements in terms of temporal and spatial discretization. You can account for complex sound phenomena, but it's usually prohibitive in terms of computation cost. That's why you have usually very small domains. And remember that you need some special acoustic treatments at the boundary conditions, at the borders of your domain. For the acoustic energy for Williamson-Hawkins, you assume free field between source and receiver, external flows mainly, and you have a sensitivity of the results to the location of the source surfaces. Okay, that's all for this presentation, which is more a reminder on the aeroacoustic methods and introducing in fact some elements on the SRS approaches. I will switch to the second presentation on broadband noise modeling. Let me check the chat window. So remember, you can ask your question if you have any in the chat window. I don't see any question at this point, so I will switch to lecture 6 on broadband noise modeling. It will be a bit quicker because you will see that these models are a bit more simple. They are not so simple in the writing, but in fact they are very simple to use. We'll have some general information about broadband noise and the available approaches to model such broadband noise contribution, and you will see that there are a large number of models, 5 models for broadband noise modeling. So when we were considering in fact direct CAA and acoustic energy methods, we are talking in fact about very time-consuming approaches. So it's very long to perform this analysis. It's very usually can be very difficult because we have some strong requirements on spatial and temporal discretization. So it's not so easy at this point. And it's not so easy. It will provide detailed acoustic information, but is it very necessary, such a detail for the acoustic information? Not always, and sometimes it can be interesting to have some qualitative information about acoustics from steady state runs calculation. So this qualitative information is usually referring to the broadband noise contribution of the flow. And the idea is, for example, to compare different noisy designs. For example, you have 2 configurations for certain shape of obstacle. You want to compare the potential noisy design compared to the silent one, and see what can be expected as a difference between these 2 noisy designs. And that kind of analysis, very qualitative, it can be done quite rapidly using these broadband noise models. So when you have noise, you have discrete and broadband. There is a small mistake here. If you remember when I was talking about dipole, in dipole you have discrete and broadband. And these 2 contributions from monopole and dipole, we are going to forget them. Here, when we do this kind of analysis for broadband noise modeling, we are only interested in the quadruple broadband noise contribution. Quadruple, I insist, quadruple broadband noise contribution. So turbulence noise typically. So broadband noise, it's a continuous spectrum. Energy is present at all frequency in a given range. It's completely different from tonal noise. And when I talk about tonal noise, I talk about discrete noise. So that is, the energy is separated and concentrated on very discrete frequencies. Tonal noise usually it's due to instabilities, coherent structures that are interacting, and so it's extremely restricted in terms of frequency band. So when you want to represent this tonal noise, usually you need to do NCD simulations. It's completely necessary. So we are not going to represent this tonal noise. We are not going to use NCD simulation. So from this approach, we can define and distinguish 2 kinds of models for broadband noise modeling. First, we are going to distinguish models that are based on average values from turbulence and flow velocity fields, for example, and model based on a fluctuating flow field that is reconstructed. And this fluctuating flow field will be representative in some kind of an acoustic contribution to the aerodynamic field. So you have 3 models in this category, 2 in this one. We'll pass rapidly on this model just to show you. In the GUI, you are you have performed your, you have converged your steady state runs calculation. Now you go inside the tree and you go to acoustics, you double click, you will have this window that will open. And here you are able to choose these broadband noise sources. And when you choose these broadband noise sources, you don't have any more choices. That is, when you select this option, you will have access to all the post-treatments that are available for the broadband noise modeling. So we'll have access to everything I will cover in this presentation. The post-treatment quantities will be available under the acoustics category. For example, inside this contours, you will see the acoustics, and if you select this one, you will have access to all the quantity we are going to talk about. So first one is Brodmann's formula. Based on turbulent quantities, it's particularly able and based on isotropic turbulence. So it's a quadruple source. You are going to consider isotropic turbulence for noise, and so we are going to use properties, local properties of turbulent fields to build some acoustic power, some acoustic measure of a volumic contribution. Because when I speak about isotropic turbulence, I'm referring to a volumic contribution, a volume in which you have some isotropic turbulence that is creating some noise because you have interaction between the eddies inside this volume. So, as a consequence, as you can imagine, you write, in fact, you define this acoustic power based on properties, on turbulent properties. And here you recognize, for example, U prime, which is in fact a turbulent velocity. You divide by S0, which is in fact the sound speed, to the power 5, and from this ratio you will be able to define an acoustic power. Since we are considering isotropic turbulence, we are considering a volume, so what you do here is a volumic integral. So you be extremely careful, you need to use a volume integrated acoustic power as an integral quantity to characterize a design. So this is exactly what is done here. The user is going to the report section of the tree, is selecting volume integral. In acoustics is selecting acoustic power for a fluid cell zone. So it's a volumic region, and then you will have a total volume integral, which will be a measure of this acoustic power by Brodmann's formula. So be careful, you need to pass through this menu and this reporting to assess the acoustic power inside the volume. And it's only a quadruple source contribution. Another example to assess the jet, coaxial jet example with an experiment. Main point I would like to say to you at this point is that you recover correct trend. That is, with this very simple model, which is a very direct post-treatment from your turbulent flow field, you will be able to have the correct trend. For example, you have the correct minimum for this acoustic power for certain wavelengths of the different acoustic property or acoustic content inside your jet. So it's quite nice. You have a discrepancy in terms of values, it's normal, but you have the correct location for the minimum of acoustic power. So it's quite nice. So this is the first model. Second model is assessment of the turbulent boundary layer noise. So here we're considering dipole noise based on Lytle-Curls integration equation from 55. If you remember, we were talking about this to consider, in fact, the influence of the wall. So when you say wall, you say, of course, a boundary layer near the wall. So this is clearly a contribution from the boundary layer. So this dipole noise contribution corresponds to a surfacing integral. We saw that earlier. And this surfacing integral is rewritten, in fact, to integrate this particularly important term, which corresponds to the time derivative of the pressure at the surface. So it's important because this term that is describing, in fact, the variation of the flow near the wall. And this variation of pressure that is going to be the generating term to create this acoustic response at the wall. So this time this is a surfacing term, so we are going to use a surface integral. Be careful. So you go to report, you calculate a surface integral for the surface acoustic power, and that will allow you to compare different designs. Same idea, but you select the surface, the whole surface corresponding to your obstacle this time. So it's a measure of a dipole noise contribution only at the source. So it's clearly defining the contribution of the wall of the source. It is not defining a quadrupole contribution, for example. So this is the purpose of the workshop 4, if I'm not mistaken, where you are going to use this model, this approach, turbulent layer noise, to compare, in fact, the intensity of potential noise emitted from the walls, which correspond to the external portion of this car, which is a sedan car, if I remember correctly. Third model, based on turbulent properties, jet noise models, is very specific to axisymmetric jets. I will not deep inside the formation, which is quite complex, so you can have a look at the reference. Only thing that I would like to stress at this point is that it's corresponding can be applied to the axisymmetric jets only. So you need to be careful. There is a strong restriction for the use of this post-treatment. Okay, so these were the first 3 models for broadband noise modeling. Second category is trying to rebuild, in fact, an acoustic field, an acoustic fluctuation field from the turbulent velocity field. And from this turbulent velocity field, we are going to rebuild, in fact, a finite sum of discrete Fourier modes that will correspond, in fact, to acoustic contribution from this field. And where you were, in fact, in the broadband noise GUI window, at some point you need to specify a number of realization to represent, in fact, the number of realization of this acoustic field to extract, in fact, mean acoustic properties from these realizations. Okay, so when you consider, in fact, the first term, we are going to use a linearized Euler equation. They are derived from the Navier-Stokes equation. We decompose the flow into a mean, a turbulent, and an acoustic component. And this time, we consider that the acoustic component are the much smaller term compared to the mean and turbulent field. So we are going to consider the terms that are the smaller inside the equation in terms of magnitude, amplitude. And this term, usually they are quite complex, because when you consider smaller terms, it's usually more complex terms. And these terms are usually corresponding to 2 contributions, shear noise and self noise. Self noise, why self? Because here you recognize that you have this fluctuating term which is interacting, which is the same fluctuating term along each component. And for shear noise, you see that you have some strong interaction between a fluctuating term and a mean term, and here between a mean term but along 2 different components. So self noise is due to a turbulence field alone. It's turbulence that is creating its own noise, and here shear noise, you see that you have an interaction between turbulence field and the mean contribution to a flow field, and an interaction between 2 mean flow components. So when you consider these 2 terms, they are source terms, and they contribute to the noise that is created inside this equation. So that was the case for a linearized Euler equation, and for Lily's equations, you have 2 contributions. Once again, it's very complicated because it's the smallest term that we are going to consider for Lily's equation. And here, once again, you recognize self noise that is involving only turbulent fluctuations only, and you recognize shear noise, where you see that you have contribution from mean flow quantity and turbulent flow quantity. And they are mixed, they are combined, and that is typically a shear noise. So these 2 contributions, remember I was talking about the number of realizations defined here, number of Fourier modes for each realization defined here, and they will be available, for example, on a contour of acoustic. You can select the tonal noise source for Lily's equations, for example. It will be available directly in the GUI. So, concluding remark, broadband noise, we were talking about the noise distributed over a broad range of frequencies. Semi-empirical correlation, like with lattice acoustic analogy, are used to get broadband noise sources for the first three models. And remember, you have access to these 5 models. The first 3 ones are typically based on local properties of the turbulence that are integrated on a volume or on a surface. And for these last 2 models, you are rebuilding, in fact, an acoustic field. And from the realizations of this acoustic field, you are going to extract mean source term corresponding, in fact, to noise, to contribution of noise, shear noise, and self-noise for both source terms in these idealized equations. Okay, at this point, I think I will stop the recording for today's session.